Welcome back. In the previous lecture, we solved the Schrödinger equation for the wave function of a qubit pair. In this lecture, we collect the algebraic properties of the two qubit observables that we need for their Heisenberg's equation of motion. So we continue the discussion of this system of two qubits with the Hamilton operator is the dot product of the two Pauli operators, which is written out here. The components x1, y1, z1 for the first sigma Pauli operator, and x2, y2, z2 for the components of the second Pauli vector operator. And there is the overall energy factor E, and we have already seen that this Hamilton operator has eigenvalues E, which occurs 3 times, and eigenvalue minus 3E, which occurs once. In the previous lecture, we looked at the Schrödinger equation that results from this dynamics, and now we want to look at the Heisenberg equations of motion. Now, that means that we want to look at, say, the time derivative of a component of one of the Pauli operators at time t, and that would be 1 over IH bar, the commutator of this component at time t, with the Hamilton operator, which is E sigma 1 at time t, sigma 2 at time t. So all operators are at time t, all are at the same time. And so we need to work out commutators of this sort, for which we back up a little bit first and look at algebraic properties of Pauli vector operators, some of which we have studied before, but we need a bit more than what we had done in the past. We first look at the Pauli vector operator for just one of the qubits, and I will just write sigma for that. And it will refer to a particular time. But there's only one time going to be involved, so I will not write the time argument. All the sigmas, all the components of sigma will be at the same time. So what we remember from previous lectures is I take two components of this Pauli vector operator, one in the direction of the numerical vector A, and one in the direction specified by the numerical vector B. So A and B are not operators, they are numbers. Then this is equal to the dot product between the two vectors A, B times the identity, plus I times the cross product of A and B dot sigma, which is just an example of the fact that we have seen multiple times that any product of sigma operators in the end is a single sigma operator. Any function of the sigma vector operator comes down to just having the sigma vector operator once and perhaps multiples of the identity. So now if I reverse A and B here, so if I look at B dot sigma, A dot sigma, then of course it's just like switching between A and B, so which makes no difference to the dot product, but it changes the sign of the cross product. And therefore, if I look at the commutator of two components of the sigma vector operator, that will be the difference of these two expressions. So it's going to be 2i A cross B dot sigma. So the commutator of two components of the Pauli vector operator, for which we write the symbol sigma, is equal to 2i times the component in the direction which is perpendicular to both A and B. What else can we do with composing sigmas? What about sigma dot sigma? Well, if we write this out, it will be the x operator squared plus the y operator squared plus the z operator squared. Each of them gives us the identity, each of the squares is the identity, so it's 3 times the identity. identity. So sigma dot sigma equals 3 times the identity. Again, we have something which involves more than one sigma. It reduces to something simpler. In this case, just a multiple of the identity. What about sigma cross sigma? No, it's not 0 because the components of sigma do not commute. So perhaps we begin by looking at the third component. So that's the third component of the cross product, which is the first component of the first vector times the second component of the second vector minus the second component of the first vector times the first component of the second vector. Well, this is a commutator of this kind, where A and B are the unit vector in the first direction and the second direction. So what we get is 2i times the unit vector in the third direction dotted into the sigma vector. So we get 2iz. The commutator of x and y is 2iz. And this, however, is 2i times the third component of the sigma vector operator. So what is true for the third component is also true for the first component and the second component. So we conclude that the cross product of two sigma vectors is equal to 2i, the sigma vector itself. Alright, so this is our collection of identities formulas for a single sigma operator. But we will need statements about two of them. So let's just apply this machinery to a more complicated situation where I have a dot sigma 1 and then I have sigma 1 dot sigma 2. Now this is very similar to this expression, except that where we had the b vector, we now have the sigma 2 vector. But the sigma 2 vector works on the second qubit. So as far as the sigma 1 vector is concerned, which is for the first qubit, this is similar to a b. It's like a number. Okay, so it commutes, the components of sigma 2 commute with the components of sigma 1. They don't talk to each other. They are referring to different things, qubit 1 and qubit 2. So as far as the algebraic properties of sigma 1 are concerned, the sigma 2 is just like such a numerical vector b. So we can use this expression, except that wherever we had b before, we now write sigma 2. So this begins with a dot sigma 2, and then there is I times, and then we have a cross sigma 2 dot sigma 1. Now let me clean this up by writing it such that we have a dot something in both expressions. A dot sigma 2, and then I want to have a dot, so I could write plus I times a dot sigma 2 cross sigma 1, just making use of the fact that in such a cross dot product, I can put the crosses and the dots anywhere I like if I keep the order of the factors as it is, or replace it by a cyclic permutation, which is allowed here because this components of sigma 1 and those of sigma 2 commute, so they are like numbers in that respect. So I can also switch to a dot sigma 2 and then have sigma 1 cross sigma 2, then I get a minus I a dot sigma 1 cross sigma 2. Right. And now what about the other order? What if I have sigma 1 dot sigma 2 and then a dot sigma 1? So it's the same operators but in the reverse order. Well, here we just get a dot sigma 2, but then we have I, and now we get sigma 2 cross a dot sigma 1, and so this is a dot sigma 2. And now I again want to have the a outside, but now taking the a outside, I will have to switch between sigma 2 and sigma 1, so I will get minus I a dot sigma 2 cross sigma 1, or if I begin here but I keep the cyclic order, then it will be A dot sigma 2 plus I A dot sigma 1 cross sigma 2. Okay, so we have this product giving us this expression. We have this product, which is the same factors but in the reverse order, giving us this expression. So in particular, we can now work out what is the commutator of A dot sigma 1 with sigma 1 dot sigma 2, which is something we will need to set up the Heisenberg equation of motion for A dot sigma 1, right? So it's this expression minus this expression. That's what the commutator says. Maybe I write this out as a reminder. So this commutator is the product as the factors come and minus the product with the order reversed. So it's exactly this expression minus this expression. So we go over here. It's this expression minus this expression. So it's negative 2I A dot sigma 1 cross sigma 2. What else could we possibly need? Well, look here. Eventually, this will give us the time derivative of A dot sigma 1, and it will involve not a component of sigma 1 or sigma 2, it will involve the component of sigma 1 cross sigma 2. So perhaps we should also work out what are the corresponding relations for components of sigma 1 cross sigma 2. So next we will look at the ingredients that we need to find the time derivative of a component of sigma 1 cross sigma 2. So we will look at A dot sigma 1 cross sigma 2 and then sigma 1 dot sigma 2. Okay, how can we do that? Well, first let's bring it into a form that is more susceptible to using some of these expressions. So let me try to bring it into one of those forms. So for that, I just make use of the property that I can rearrange terms here, and I will begin with A cross sigma 1 dot sigma 2, and then sigma 1 dot sigma 2. And this is now an expression of this kind, where the sigma that appears here is the sigma 2, and the A that appears here is the A cross sigma 1, and the B that appears here is the sigma 1 here. So in writing A dot B, I have the dot product of A cross sigma 1 and then B, which is another sigma 1. And then I have plus I, and then I have the cross product of what is A and B here, and that's A cross sigma 1 and sigma 1 there. A cross sigma 1 cross sigma 1, and then this is dotted into sigma 2. So in writing this, I was rather careful in making sure that the A cross sigma 1 operator that stands here to the left of this sigma 1 operator that's all by itself, that remains on the left. So in this dot product, I wrote A cross B1, A cross the sigma 1 dot sigma 1 rather than the other order. Order doesn't matter if these are just numbers, but if they themselves are operators, I have to watch out. And also in the cross product, I made sure that what is the A vector here, which is the A cross sigma 1 vector operator in this application, and the B vector here, which is the sigma 1 vector operator in this operation, that they remain in the same order. Now this is a double cross product. So it has one component in the direction of this sigma 1, multiplied by the dot product between this vector and this vector. Again, I pay attention to the order in which things appear. So I have to write this sigma 1 first, and then the dot product between this vector and this vector, A dot sigma 1. And so just to be clear, the sigma 1 that appears here is this sigma 1, and the sigma 1 that appears is this sigma 1, which is dotted into the A. And then there's a second term, a negative, and that's in the direction of A, and has the dot product of these two sigmas, sigma 1 dot sigma 1. But sigma 1 dot sigma 1, that's of this kind. So that is just 3 times the identity. So this is sigma 1 and then A dot sigma 1, and then we have minus 3 times A. Okay, and what do we have here? Well, here we can again make use of the fact that in this cross dot product, I can put the dots and the crosses where I want, as long as I keep the order of the vectors the same. So this is equal to A dot sigma 1 cross sigma 1. And the sigma 1 cross sigma 1 is of this form, sigma cross sigma. That will give 2i A dot sigma 1. And now we put these things together by just collecting all the terms. So I begin with the 2i A dot sigma 1. I just copy from here. Then here we have I times, and now what we have worked out here, which is this expression, has to be dotted into sigma 2. So let's just see. So there's the sigma 1 here that gets dotted into the sigma 2. This sigma 2 commutes with the A dot sigma 1. So I can just write it as sigma 1 dot sigma 2 and then copy the A dot sigma 1 from here, or from here. And then we have minus 3A, which is dotted into the sigma 2, minus 3A dot sigma 2. So here we meet an expression that we have worked out already. It's written here, sigma 1 dot sigma 2, A dot sigma 1. And that's A dot sigma 2 plus I times A dot sigma 1 cross sigma 2. And so we now combine these terms into the following. I begin with 2i A dot sigma 1, 2i A dot sigma 1, and then I see here a negative 3i A dot sigma 2, I from here, negative 3 from there. And there is another plus I A dot sigma 2 from there. So together I have negative 2i sigma 2. So I just get negative 2ia dot sigma 2. I repeat, there is a negative 3ia dot sigma 2 from this I times this term, but there is in this term there's another positive I dot sigma 2. So again, together it's negative 2ia dot sigma 2, which I combine together with the 2ia dot sigma 1 that we have already found. And in addition, we have this term which just gets multiplied by I, so we have an I squared, and that gives us a negative A dot sigma 1 cross sigma 2. So we have now worked out this product. What about the product with the operators in the reverse order? What about sigma 1 dot sigma 2 and then A dot sigma 1 cross sigma 2? So of course we could go through the same kind of reasoning again, but we could also recognize that this operator is just the adjoint of this operator. Because if I take the adjoint of this operator, the A is real, then this Hermitian operator just comes up front, and the second Hermitian operator just goes to the rear. So I can just take the adjoint of this expression to get this expression, which means that this is equal to taking the adjoint here. Okay, so taking the adjoint will give me minus 2ia dot sigma 1 minus sigma 2, and then minus a dot sigma 1 cross sigma 2. Right? And therefore, if I want to have the commutator of a dot sigma 1 cross sigma 2 with sigma 1 dot sigma 2, and for this commutator I have to take this product minus this product, which means I have to take this expression minus this expression. And then the a dot sigma 1 plus sigma 2 just cancels, and in the difference I get 4ia dot sigma 1 minus sigma 2. So after all this preparatory work, we are now ready to write down the equations of motion, the Heisenberg equations of motions for components of the two sigma operators. So I remind you that the general expression is the time derivative of an operator, and I will not write all the arguments, is the parametric time derivative plus the dynamical time derivative, which we get as the commutator of the operator with the Hamilton operator. So the Hamilton operator is this in our example, and for f we will use a dot sigma 1, a component of sigma 1, and a dot sigma 2, the corresponding component of sigma 2. And since a is general, it is as if we were just using sigma vector as a variable, but it's easier to talk about components. So a is a numerical vector that we can choose any way we like. We can choose it as the unit vector in the x direction, y direction, z direction, or some other direction. It doesn't really matter. So it's an arbitrary vector which will not be important, but it will just help us to set up the equations. So I'm looking at the time derivative of a dot sigma 1, and what do I get? Well, the a, of course, we do not choose time dependent, so we do not introduce a parametric time dependence by making a also time dependent. Now, a is a fixed direction, and the only time dependence comes from the dynamics that changes sigma 1 at one time to sigma 1 at a different time, or sigma 2 at one time to sigma 2 at a different time. So we only have this contribution. So we have 1 over I h bar, and then it's the commutator of a dot sigma 1, and then e sigma 1 dot sigma 2. And so what is that? Well, the e comes out because it's just a number, and then we have the commutator that we have worked out here. So it's negative 2i, and then a dot sigma 1 cross sigma 2. So the I cancels, and we have negative 2e divided by h bar, and then a dot sigma 1 cross sigma 2. Now what about the time derivative of a dot sigma 2? Again, it's 1 over I h bar, a dot sigma 2, then e sigma 1 dot sigma 2, the commutator with the Hamilton operator. And now we go from here to here by just interchanging sigma 1 and sigma 2. It changes sigma 1 to sigma 2, and here in this dot product whether it's sigma 1 dot sigma 2 or sigma 2 dot sigma 1, that's the same, sigma 1 dot sigma 2. So we go from here to here by just interchanging sigma 1 and sigma 2. But if I interchange sigma 1 and sigma 2 here, I get a minus sign. So this will be plus 2e divided by h bar a dot sigma 1 cross sigma 2. So the time derivative of a common component of sigma 1 is a certain expression. The time derivative of the corresponding component of sigma 2 is negative that expression. From here we see immediately that the time derivative of a component of the sum of sigma 1 and sigma 2, which is adding these two expressions, so the time derivative of a component of the sum of sigma 1 and sigma 2, but that is 0. Sigma 1 plus a sigma 2 do not depend on time. So the time derivative of sigma 1 sigma 2 involves sigma 1 cross sigma 2. So we cannot solve these equations if we do not also know something about the time derivative of sigma 1 cross sigma 2. So let's look at that. So what's the time derivative of A dot sigma 1 cross sigma 2? By the same token, this is 1 over IH bar, A dot sigma 1 cross sigma 2, and then the Hamilton operator, so there is a factor of E, and then sigma 1 dot sigma 2, which we have worked out here. So this will just give us 4E divided by H bar. The 4 from here, the I cancels this I, and then we have A dot sigma 1 minus the sigma 2. And so now we have all the equations that we need to find the time derivative of sigma 1 and sigma 2 in terms of what they are at the initial time. In summary, we established the properties of the two qubit observables, essentially two sets of Pauli operators. In the next lecture, we use this machinery for studying the Heisenberg's equation of motion.